Excuse me, sir.
Yes.
So, in a couple of days back, ERP has taken the choices from the students regarding if they want to give the online or the offline exams option. Uh, but
For for labs, it is not applicable.
okay, okay, sir.
No NSEM for lab.
So you
Okay,
have one lab test next Tuesday, 5th April. You send a mail, and that will be purely online, same logistics as the first lab test. In Moodle, exactly the same logistics.
It's just a lab test. It's like an NSEM, but it's not an NSEM. I mean, theoretical.
No, forget about NSEMs and all. It's
Yeah,
just another lab
it has
test.
nothing to do with NSEM.
Labs never have an NSEM. Even when it
Yeah.
is in offline mode, labs never have an NSEM. Labs always finish before the offline exam start. So that option has no relevance for the systems programming.
thank you, sir.
Okay. Yeah.
So, sir, will the timing be the same?
We'll announce that.
Okay, sir.
In the class hour, but exact timings we will let you know in the mail.
Okay, sir.
I mean, exact timing, total time, and all these things.
Yeah, it will be within the 2 to 5 slot that you have for the systems programming lab next week.
We can, for the time being, say at most, not at most, somewhere around 1 hour. Plus,
No, that all that we'll announce. I'm saying that
yeah,
it will be somewhere within that slot. Basically,
yes.
2 to 5 you should keep
Okay, sir.
busy. We'll announce when to start, how long, and everything we'll tell.
We will let you know. We have not decided all these things ourselves. Anyway. Okay. So, so today we will cover the last topics of this course, that is about shell programming. In particular, what I will do to conclude this exposition to shell programming is just I will tell you the control structures and see some few examples. Okay, so I share my screen. I hope it is visible. The red border has come today. Okay, so this is this. Okay, so far you have seen most of the shell features, variables, arrays, functions, arithmetic expressions, and also you have seen some conditions. So now we will just fill out the remaining details, that is conditional statements and loops. Okay, so conditional statements essentially means if then loops, if then else loop, if else if, else if, else if, else loops. Okay, how we can uh, code these things in the language of Bash. Okay, so the summary of these statements, or in other words, the syntaxes are listed here in this slide. So you tell a condition. Condition we have seen in the last class. So if condition, this semicolon is mandatory, then you do some statement 1, statement 2, statement 3, statement 10, and the same if condition must end with this 5. Okay, so this is a peculiar syntax. In particular, I do not know if you already give then what is the necessity of this semicolon, but it is mandatory. Okay, because then essentially terminates condition. Okay, so you need this semicolon. It's not very clear to me, but anyway, whatever be the reason, if you want to write syntactically valid shell programs, you have to follow this syntax. So this is plain one-way conditional statement. And then you have if-else statements. If condition, semicolon, then statement 1, statement 2, statement 3, else, statement 1, statement 2, statement n. And eventually you should end this if, the scope of if, by fi. Likewise, you can have else if. Okay, so one thing is this, each semicolon can be substituted by a new line. So for example, if you write this then on a new line, then this semicolon is not necessary. Otherwise, the semicolon is there. So you can write if condition in the next line, then in the next line C1, in the next line C2, in the next line C3, and so on. After mth line CM, and then again 5 in a new line. Okay. So for example, this you can write it this way. First one, if condition, then C1, C2, and so on, CM, else this 5. Okay. So that's it. And you also have if condition 1, then block 1. Else if is abbreviated as elif. So you cannot write else space if. You have to do something like elif. Condition 2, then block 2, elif. Condition 3, then block 3, and so on. And finally else block R. Now once again, this if condition must end with fi. Okay. And you also have an equivalent case statement, case value in val 1, block 1, double semicolon basically terminates the scope of this first value, whatever is done. Val 2, block 2, so double semicolon, like val n, block n. And you can also have this star, which essentially stands for default block. And you have to end this case statement using this case in reverse, Isaac or something like that. Okay. So this double semicolon is necessary between different values. Okay. So we will see examples to clarify these things. And unlike C, it is not like, let's say, value 2, this condition is satisfied. So you go to block 2, then block 3, block 4, block 5. This is not the behavior. Only up to only block 2 is executed. So no explicit breaking is necessary. Okay. And note the use of semicolons here, double semicolons. Every condition must be followed by a semicolon. Okay, so case is not exactly covered by semicolon because this case is based upon certain values. No need to have a semicolon after then, else, or elif. Okay. Use the semicolon before this if it appears in the same line as the preceding block. And a double semicolon is needed before every case option, starting from the second, of course. Okay. And we will see examples where if val 1, it looks like a single value, but you may have multiple values here. Okay. These things you can separate by this or. Okay, so you will see examples. And in all the cases, whenever some conditions are involved, these conditions are essentially stored in the variable $? And bash silently looks at the special variable and proceeds accordingly, whether this condition is satisfied or not. Okay, so you do not have to do anything. You do not have to explicitly access delta ? and do something based upon that. Okay. Okay, so let us see an example. Okay, so you essentially want to figure out what kind of file the user wants to talk about. So the user runs this checkfile.sh with one command line argument. If the number of arguments is 0, then you say that run with one command line argument and exit. So it's a simple if statement. Okay, ended by 5. Then the first command line argument. Now, if this code comes here, that means $hash is greater than 0. So $1 makes sense. This is the first command line argument. Okay. And there you say, if not exists this file name, then you simply say this file name does not exist and maybe exit 2. Okay. Else I want to find out what kind of file it is. So this is an example of if-else statement. Okay, so then you see inside this. So if you are in this block, you know that the user has supplied a file name and it does exist. Okay. Then you check whether it's a regular file. Then you say it's a regular file. And I am basically quoting this double quote. That is why I am using this. I am taking this literal double quotes here. So I am escaping this using this backslash. Otherwise, if it is a directory, then you say this file name is a directory. Otherwise, it is neither a regular file nor a directory. So this is an example of if, elif, else statement. Okay. Then you look at the permissions. If this file is readable, you write read. If it is writable, you write write. If it is executable, you write execute. And in this case, the entire if command is given in a single line. Therefore, this semicolon is necessary. The semicolon is also necessary. Okay. This is a simple-minded shell script that illustrates how you use this conditional, this branching kind of thing. So let us see some examples. So if you run this without any argument, it will say run with one command line argument. And then if you run it with something like this file name, you can also give. Then this says that it is a regular file and you have read, write, execute permission. Okay. Then if you run it with /user and you know it is a directory, this also says this is a directory and you have read and execute permissions, you do not have write permissions. And similarly, SQL. Oh, I see. Yeah, there should be a tilde SQL. Okay, I'll note down. This is because in LaTeX tilde means an unbreakable space. So that's the problem. So this is okay, so there should be a tilde here. Tilde /SQL. Okay. The tilde is absorbed as a space in LaTeX. Anyway, so this is a directory and its permissions are read write directory. Likewise, if you look at this /dev directory, you will find there are many devices and these devices are files, but they are not regular files. They are not directories. They are essentially called devices. Okay. So whatever a device is, you do not for the moment need to know. There are file types which are neither regular files nor directories, like device, like sockets. Many things are there. Okay. And so this is neither a regular file, not a directory, and the permissions are read and write. Execute permission is not there. Okay, so let me know if you have any question about this. No, anyway, it's okay because this is a very simple-minded program. And then this is an example of, let's say, case. Okay. So you want to search for word 1 or word 2 or word 3. So you can supply either one word or 2 words or 3 words. And you want to find out whether these things, either this or this or this, you want to run grep on this file name. Okay. You want to run grep on this file name and word 1, word 2, word 3, these things you will supply depending on how many words you are trying to find out. Okay. how many lines in the file name that match 1, 2, or 3 words. Okay, so if it is 1, you simply say you should specify 1, 2, or 3 words. If there is no command line argument at all, then you are not even specifying this file name. So you just say usage and this prompt. Otherwise, multiple things, that is multiple patterns may be searched using multiple -e things. So if there is only 2 things, then $1 is anyway stored as file name. So you are searching for the output of grep on this keyword, and if it is 3, you say this is I am searching for word 2 or word 3, or rather I would say word 1 or word 2. Sorry. And if this is 3, if $hash is 4, then there are 3 words. So you make -e$2, -e$3, -e$4 file name. Otherwise, if the number of command line arguments is 5, 6, 7, 8, whatever, it simply equals too many words giving up. And you see that ASAC basically ends this case statement. Okay. And you also see that every case block is delimited by a double semicolon. Okay. And here C is populated only when this is 2 or 3 or 4. This does not set C. This does not set C. So whenever you say if $C, this means whether this is defined or not as a string. If it is defined, this means it is set by this, or this, then echo this. These many lines matched. Now you see that I have run grep by -c option. So that essentially counts how many lines match. So this C will get a count. Okay, so you recall that grep works that way, how many lines match, rather than the lines themselves. Okay, so this is running grep with the count option. And these are the patterns, regular expressions. Expression $2 or $2, $3 or $2 or $3 or $4, something like that. So if I run it without any argument, this should execute. So usage, you run it, give a file name, then a word 1, possibly a word 2, and then possibly a word 3. And if you run it with a single this, $hash is 1, then this is executed. So it says that you should specify 1, 2, or 3 words. So let us do it. So you will look at this file, text file.txt, which appeared earlier. So if you run it with only problem as the word that you search, you see that 2 lines match. If you run with problem and algorithm, that means any line which matches problem or algorithm is reported and counted, so it gets the value 7. And 3 keywords I give, problem, algorithm, and method, 12 lines match. And if you give something like a 4th thing, problem, algorithm, method, protocol, then this will be executed. Too many words giving up. And since SC is not defined here, it is not printing anything here. Fine. Again, I think this is a very simple example which just illustrates the syntax of case statements. Happy? Actually, I think there is nothing to be unhappy about. It's a very simple code, just illustrates the syntax. Okay. So now what I explained to you is functions in tandem with if conditions. So this is the standard recursive Fibonacci number generator. And this program basically returns within quote values by echoing it. Okay, so this thing echo minus n, enter n, read n, and you say dollar f of dollar n is equal to whatever this is printed, whatever it echoes, this will simply come here. So now let us look at the Fibonacci function implementation. As you recall, this function keyword is not very necessary, but I usually do it in order to make these things look very, more readable. So this should always be run with one argument, which is available as $1. So you use n as a local variable, set it to $1. If it is less than equal to 1, then you simply say, of course, there is one thing, if it is less than 0, you may return 0 or something like that. So I assume that n is greater than equal to 0. This function is based upon that assumption. Then you simply echo $n and return 0. This is actually not very needed. You can also simply say return. Okay. This return statement is necessary. Since this is successful, you should better return 0. But return statement is necessary because without this return statement, this thing will be executed. And that is not the correct thing. Okay, this is very similar to as in your C functions. Otherwise, if n is greater than equal to 2, then this is called on n minus 1. Whatever is echoed, that is added to. This is called whatever is echoed, that is taken here. And then these two echoed values are added. Okay. And this added value is echoed. Okay. So here, of course, you have an if then statement here. You can also write it as else something, but I chose to return because return and exit work exactly as in C programs. Only thing is you should not give it in possibly that is not allowed. We'll try it out anyway. Doesn't matter. Return 0 and so on. Okay. So first of all, in addition to this if then else, within quotes returning by printing or by echoing, which I have extensively used here, should be clear to you. If you have any questions, let me know. No? No questions? Maybe no. And here is the obvious thing that you would see. For 0, it is 0. For 1, this is 1. For 5, it is 5, 10, 55, 16, 987. Now, what you will see and what is obvious is that this recursive way of computing Fibonacci numbers is very inefficient because it makes too many recursive calls. And it's recursive. Whenever you make a recursive call, you also have the additional burden of making an addition, a sum. Okay. So if you run it for 16, you will see a visible lag after this enter and after this printing. And if it is something like 20 or 30, essentially it will look like the program has a hang. But it actually didn't hang, or it is taking too much time for this computation, which is inefficient anyway. So one way of, I would say, removing this inefficiency is by using memoization. Right. So I use some array, and whenever some value is calculated, I will store that thing in that array. Next time when the same recursive call is made, I will simply return the array element instead of making further recursive calls. Okay, so this is memoization. You should all know this. Okay, so I try to use this memoization idea in this recursive function. Okay, but as this header says that this is a failed attempt. Okay, so what I do, I use an array, initialize 0th indexed element to 0 and the first indexed element to 1. Okay, then like this, I am calling $5. So this is the same as in the previous case. Now let us look at this rewritten value of this fib, rewritten code for this fib. Local n equal to $1, which is same. Then what it does, if $n, that nth element of that Fibonacci array is not defined, it is the 0 string, then I make a recursive call and store the final computed value in $n. And if it is already defined, nothing is done. And then I am echoing $f, $n. Okay, so this is the syntax. Because $f without this will not be treated correctly. Okay. This is fine. Yes or no? Here return is via echoing. The two echoed values are added and that sum is used to set the nth element in that array. Okay. Now you run it on several values like 0, 1, 2, 3. You will get the correct answer always. But you will see that this code is equally as slow as the previous code. Maybe a tiny bit slower, but this tiny bit decrease in speed perhaps you cannot figure out. But if this on 16 this takes something like 10 seconds, this will also take something like 10 seconds. More importantly, when after printing, if I print this F array, okay, I have computed this F array up to 16. So whenever I print that F array and the indices for which this F values are defined, I will see it does not change. It remains 0, 1. So what happened to the 0, 1, 1, 2, 3, 5, 8, the remaining things that are computed and stored in this array? What happened to them? Can you tell me the solution? What happened to them? I don't know. Why is there such a silence? So why did the F array did not change? Why did this array not change at all? Any idea? And in fact, it is because of the fact that this array F does not change is responsible for the slowness of this F16 calculation. Why? No answer.
Sir, is it like since its values nothing, it keeps going to the previous elements?
Okay?
Since
Yeah.
the value doesn't exist in the array, it keeps going to the previous element, so it is again becomes recursive.
No, but you can see that Fn is set. If it is not defined, it is set. After that, it should be defined, right?
Yes.
Sir, is it because it opens in another subshell?
Yes. At last, the correct answer came. So, do you remember maybe in the previous class or the previous to previous class, I showed by demonstrating something. I printed C square, CSQR. The value of CSQR did not change. Do you remember that example?
Yes, sir.
Exactly the same thing is happening here. Every invocation of a command using this backward code thing opens a new subshell. This is executed in that new subshell. Whatever is done to your variables is not visible. Okay. So if I look at this opens a new subshell. In that subshell, this $n-1, okay, n minus fn minus 1 is set. Okay. But when you come here, fn minus 1 is not set. It happened in a subshell. In fact, that command is supposed to set fn minus 2 also. Okay. This one. This sets n minus 2, n minus 3, n minus 3, everything. But whenever it makes this recursive call, it does not see that this n minus 2th element is set. So once again, it sets it, computes it and sets it. Okay. That is the reason I call it a failed attempt. This actually does not do memoization. It pretends to do, but because of the intricacy in shell programming, it actually fails to do that. So don't forget this backport type of things, returning by echoing, opens a new shell. Whatever changes you make, that is invisible to this shell. Okay, so how do you repair it? Okay, so I will actually not call, I will not, anyway you see that I am using a global variable f, initialized to 0, 1. Okay. And that global variable can store the value of f0, f1, f2, f3, f4, f5, all these things. I do not immediately need to print it. Agree? So what I do, I initialize that array to 0, 1. Okay, this is just the echoing the array values and the indices. Then I call. Okay, this call will run in the current shell without opening a new shell. So now whatever change you make in your function, those things are reflected because everything is happening in this shell, right? So if this is not defined, you call n minus 1 recursively, n minus 2 recursively, and these calls have a side effect. Okay, the side effect is that fn minus 1 is populated, fn minus 2 is populated, if not already populated. If it is already populated, then this block is not executed at all. If it is already defined. So after this recursive calls, fn minus 1 has a value, fn minus 2 has a value, add them and store them in f$n as an nth element. So all the computations are happening in this shell and no subshell is opened. And anyway, eventually your nth Fibonacci number will be stored here. F nth element. You print it. Now you see it prints something like 987. Also, if you now want to see the value stored in this F array and the indices, you can now see the complete list 0 to 16. 0, 1, 1, 2, 3, 5, 8, 13, 21 up to 987, and this is defined for 0, 1, 2, 3 up to 16. Clear? So be very, very careful. This backport kind of thing gives you a lot of flexibility, but you should understand its limitations. So here, returning a value is not by echoing, but by storing in the global array F. These two are different, right? Understood? Yes or no?
Yes.
Okay. Okay. Yes? Any question? Okay, possibly no. Anyway, this is another example. Not very I would say a serious thing, except only that it demonstrates multiple options, multiple values in case. I'll leave it to you. Okay. Here I have used echo kind of thing. Yes. If the length of the string is the 0 or 1, simply echo it. Otherwise, take the entire string up to or exclude only the last element, reverse it and print it, and then you print the last element. Okay. Actually, this echoing is stored in T. So we print the last element of S and then whatever is stored in T. Okay. And you can see this is what. Okay. So this just demonstrates this 0 or 1, this option. Okay. So you go through it. So that essentially covers all the examples on these conditional statements along with other intricacies. Now let us look at the looping structures. Okay. Okay, any questions up to this point? Yeah, perhaps no. Fine. Fine. So let's now look at this looping structures. For loop, while loop, and all that stuff. Okay. So there are several types of for loops. So for item in list, semicolon, do, block, done. For loop starts with one possible way of this is for item in list. So list contains element 1, element 2, element 3, element 4, and so on. They must be separated by spaces or the internal field separator to be more precise. Do block, done. Okay. So this kind of thing is not available in C, although it is available in awk, when this list essentially corresponds to an associative array. Okay, here also it can be, list can come from an associative array, but you can also specify the list in other ways. Okay. Okay, for argument, do block, done. And if you do not have this in list, it is basically in all arguments. So this is $1, $2, $3, $4, and so on. Do block, done. Okay, so in list, if it is omitted, it is always assumed to be in $at. Set of all command line arguments separated by spaces. This is a for the I would say native for statement for bash. This is still not exactly like for I equal to 0, I less than n plus plus I. This kind of for loops you can write. We will see a little later. But you can always convert those kind of for loops to equivalent while loops. So you say I equal to 0 while I less than n, then do something and then plus plus I as the last statement of that block. Okay. So this can be done using while condition is true. As long as condition is true, do block, then done. And there is another thing, until condition, do block, done. So while loops are iterated as long as condition is true, and until loops are iterated as long as condition is false. Okay, C does not have a syntax of until loops, but some other programming languages do have. Pascal has, and I think Perl has. Okay, Bash also has this until loops. This is also a loop, but this will iterate as long as this condition is false. Okay. Anyway, these are just syntaxes. And again, some semicolons may be omitted for item in list. And if you write do on the next line, then the semicolon may be omitted, then block, done. Okay. Fine, right? These are just syntaxes. And the thing is that break, continue, and exit work in the usual way. Whatever this break, continue, and exit does in connection with C programs, the behavior here is exactly the same. Okay. Okay, so let's look at a simple example. So each of the following loops prints 0 through 9 in that order, 1 in each line. Okay. So you can simply say for n in 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 echo $n. Done. This is a list, not an array. Okay. An array should be specified by additionally a pair of parentheses. It's just a list separated by semicolon, separated by spaces. Okay. Okay. Now this print can be done in this special fashion within a pair of matching curly brackets. You say 0.9, do echo n. Okay. So this essentially will produce this list 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 separated by spaces. Do echo $n, done. Okay. But there is one important thing about this notation is that you cannot use variables here or here. It has to be constant to constant. So you cannot use variables here. So echo $i ... this is not valid. Okay. So you need to know the exact value of the first element in that list and the last element in that list. Anyway, but you can use variables if you use while loops, n equal to 0, while n is less than equal to 10 or less than 10, echo n and increment n. Done. Okay. And you can also write it as until statement, set n equal to 0. As long as this n equal to 10 is false, echo it, increment n by 1. Done. Okay. Yeah, do not quote the list in this for loop because a quoted thing stands for a single item. This is one thing. The range I.J can be specified only for constant values of I and j. You cannot use variables here. Okay, and so on. So these are just ways of These are some explanations of different types of loop. Then what I will do, I will give you more, I would say, meaningful examples. So an iterative Fibonacci number calculator. Okay, so this program does this. Okay, it maintains an array. F0 stores F0, F1 stores F1, F2 stores F2, and so on for some n. Okay. Now n is initialized to 1 and f is initialized to store 0 at index 0 and 1 at index 1. Okay. And in a loop, the script asks for entering n. The nth, smallest nth Fibonacci number needs to be computed. Okay. And the loop continues until the user enters a non-negative value for n. Whenever they enter, the user enters a negative value, the loop is broken. Now, this array is maintained from index 0 to index n. Therefore, if the value of n entered by the user is less than equal to n, then f of n, this value is already stored in the array element fn. That is simply read from the array and displayed. And if small n is bigger than capital N, then fn plus 1, fn plus 2 up to fn is computed. And this n is now set to the small n. And this fn value is displayed by equal. And then once again you come to the top of the loop, enter the next value of small n, and so on. Fine. Okay. After this, the user asks whether she wants to continue. If not, the script terminates. Okay. No, the breaking of the loop is here. The user said, I want to continue, and keeps on giving negative integers. So there is a local loop here. This loop will wait until the user enters a non-negative value. Okay, so this is not the termination of the loop. Okay, this is the termination of the loop. Okay, so let's look at the script for this. Okay. So this compute rest is called in this situation when n is greater than capital N. Okay. So this takes two things, small n and this capital N. This capital N I am not storing anywhere. It's already stored in $2, while small n is less than equal to this capital N. To compute this and store in this array, increment n, done. Initialize this array f to 0, 1 and capital N to 1. Okay. Okay. So on the top of the loop, this is basically the infinite loop. So as long as this is true, or as long as it is not explicitly broken somewhere else, okay, you say enter n. If n is less than 0, then you say enter a positive integer, continue. This is not a while statement. So this continue pertains to this loop, right? Once again, you go to the top of the loop, just ignoring the remaining part of the body of this loop. Now, okay. So now suppose that n is greater than equal to 0, and therefore this condition is not executed. So the code has come here. Okay. And if the new value of n that is entered by the user is greater than n, then you need to call this compute rest. Okay. So up to fn it is computed. So you are computing from n plus 1 to this new value of n that the user entered. After this, n is set to $n, small n, and so on. And then finally, you know fn is ready, print it. Okay. Then there is a loop. Okay. This is basically an until loop. And as this is an until false loop, like this while true loop, this is basically an infinite loop. Okay. So you just ask the user yes or no. So read response. If response is yes or capital Y, then break. So this break will break which loop? This loop, right? Not this loop. So break always refers to the innermost loop. So this is the innermost loop here, until false loop. So it will be broken. So once again, you go to the top of this outer loop. And if the user says no, otherwise, in that case, the code should exit. So exit 0 after printing something like by. And if the response is nothing like yes or no, it will keep on asking for the next response. Fine. Does the code has any problem? Okay, so it's just a small demonstration of loops. Okay, it's a very simple program and it's essentially very, I would say, similar to C programs, but you start with C programs. I mean, the translation of C programs to shell scripts. Later, we will see more complicated examples where you can do a lot of things, which is not that easy to do in C programs. So this is basically a translation of a C program, a PDF-like code, right? Only thing it is written is the shell syntax, bash syntax. Okay. So F0 and F1 are initially computed. So if the value is 16, F2 through F16 are computed. It is printed. Repeat, yes. 32, then 17 to 32 are computed. Its value is printed. Repeat, yes. 64, F30 64 is computed. This is printed. And you see, if you give something like U, invalid response, retry, yes. Enter minus 40, enter a positive integer, enter 40. Now up to 64 it is computed, so F40 is already there. So it is printed. No, bye. And then dollar prompt comes. Okay. This looks so like C code. I don't think it requires further explanation. This is something which is very difficult to do. Of course, it is doable in C, but it is something like it is how many 20-25 lines of code. If you want to write this in C, it will be maybe 200, 300, 400 lines of code, and you have to use some special library. Okay, for reading directories. Okay, it's doable in C, but it's difficult. So what I want to do can be illustrated by this. Let us, okay, see this. I want to find a directory tree under user local. Okay. So on the top of the tree, I have user local. Then I have this subdirectories bin, etc, games, include, lib, man, sbin, share, source, winfig. Okay. Under this user local lib, there is a subdirectory Python 3.8. And under this, there is something, a subdirectory of this main. Okay. And in share also I have this. In etc or in games or in include, there are no subdirectories. Okay. So it prints nothing. So it's printing only directories, not files. Okay, so this is a directory tree. Under shared, this is a subdirectory, this is a subdirectory, and this is a subdirectory of this. subdirectory, 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 subdirectories of this, and so on. And for some reason, you do not have permission to explore further. Okay, although there is something under this, so you just specify I am unable to explore further. So this is the entire directory tree. Up to this point you can see, and then whatever the subtree of it is not under your permission. Okay, so you just specify the message that I am unable to explore further and stop. Of course, it is, I would say, for a reason it happened in the end. Okay, but it need not be. It is possible that this declaration, this directory also does not have permission for exploring further. So you also print it here. It's not that it's only happening in the end. Okay. It is happening because this W, it starts with W. Okay. D, E, G, I, L, W comes at the end. So that's why it is happening like that. Okay. So the output is going to be clear, right? What I am trying to achieve. Yes or no? अरे कुछ तो बोलो. This is fine, right? This is what I want to achieve. So now let us look at the code. As you can see, I have to write a recursive code that recurs on subdirectories, 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 and so on. Okay. Okay.
Yes,
so let us just code. Okay. If you run without any argument, simply call directory tree.sh. Then I assume the root directory is dot. Like when you say ls without any argument, it essentially means list the files in the current directory. So here also I will do the same thing. Otherwise, I will take the value of the first argument and set that as root directory. Okay. And now I have a value for root directory in all cases. If it happens that this is not a directory at all, then you say that this is not a directory, exit 1. Fine. Okay. Otherwise, you call this explode did function. And here you see, depending upon whether it's a root directory or a subdirectory or a sub-subdirectory or a sub-sub-subdirectory, the amount of space that you print, that depends, right? So along with the current directory, I also specify or send as a parameter the level of that directory in the directory tree. Okay, so that a correct number of spaces can be printed. Okay, the indentation is correct. Otherwise, everything is look like user local bin, user local entity, just a flat list. The tree structure is not apparent, right? So the root directory is at level 0. I am passing this thing. Okay. Then $1 is this, $2 is this. So current directory is read from $1, current level is read from $2, and the local is another local variable level. Okay. So as long as this level is less than current level, I will keep on adding some spaces. So here I actually have added 8 spaces, but it may be 4 spaces, 3 spaces, tab, whatever. Okay. So this prints the spaces. Then it echoes the current directory. Okay. If that directory, current directory, is not readable or executable, okay, then you say unable to explore further. Okay. It's not readable means what? You cannot read the directory content. And if it is not -x, that means what? You cannot go to that subdirectory. Okay, so in either case, I'd say unable to explore further, and that's all. This will be something like this line. Appropriate number of space is printed, then the directory is printed, and then you see that you cannot explore further, so you do it and go back. Okay. Otherwise, okay. Otherwise, you do not have to print this, unable to explore further, and you go to subdirectories. So this echo essentially brings a new line. Other earlier prints are all -n, and this is not -n. So that exploration stops. That's where exploration stops. So you do not need to this echo without -n. So that line is over. But if you can explore further, you have given some space here, and you have printed up to this without a new line. This echo introduces the new line. Then this is the very important thing that you need to understand. ls $current directory. You take a listing of all files in the current directory. Okay. And for each entry in that directory listing, do. If current directory by $entry is a directory, then you recursively go to that subdirectory. Okay. With the level increased by 1. If it is a normal file, not a directory, or it is not a directory, then do not make any recursive call. And so on. That's it. This is simple, right? This is simple in if you do shell programming. If you're interested, you may figure out how you can write this code in C. It is doable, I know. Okay, so what do you understand? You can use the directory listing as a list and iterate over every entry in that list. So if that thing is a directory, then you make a recursive, you go to that directory, make a recursive call there. Otherwise, do nothing. Happy or not?
Yes.
Okay, good. This is perhaps, I would say, the first shell program of a natural type. This is a natural problem for which we write shell programs. Okay. Okay, so I will give you a few examples, but you have seen that this bash loops are somewhat different looking than C loops. But you can also use C loops using this, like this, for but you have to specify this thing like this: I equal to 0, I less than 10, plus I, do echo $I. And you can also have this: I equal to 0 while this, do echo $I, plus I. Okay. This is the arithmetic evaluation, but it also supports this kind of structures. Okay. And this is not, I would say, a very useful program, but this, I would say, demonstrates two concepts. Actually, many concepts. Okay. Anyway, this is a good example. So far, you have seen that read something from the terminal. And terminal means stdin. So if I do something like this, if I want to read from a file called file name, fname, then I have to use this read statement in a loop. Okay. And the input comes from fname. And I store the individual lines of this fname in an array called L. It's initialized to the empty array. Every time I read a line, I append that array by this single entry $line. Okay, and then they will say these many lines are read. And of course, I can do it if it is a regular file and is readable. Okay. If it is not a regular file, there is no point reading lines one by one from that file. And if it is not readable, you cannot do it. And I am doing it again in a loop for fname in $@. But as we have seen that if we do not use this word in $@, this is the default thing. So I can just say for fname do. Happy? So let's say I run this file to array.sh on $SPL by probe by libstack by star. Okay, and you recall that before this is called, okay, the shell expands the star by all possible matches. And under this directory, there are actually 3 files, makefile, a subdirectory shared, a subdirectory static. Okay. So what the shell does, it will replace this by $by home of it or home foobar, whatever, libstack, makefile, home of which SPL proc libstack shared. Okay. So this star substitution is done by the shell. And if you want to prevent that substitution, then you have to quote it, okay, using double quotes. But then this program will take that star thing as a literal thing. It will try to find a file with name star. That is wrong, right? So if you allow these wildcards inside your function, inside your shell scripts, you should have some, I would say, some way to make meaning out of this. It's possible. This star is not expanded by the shell, but by your code. That is also possible. But anyway, I hope I have not quoted it. So the shell will actually create 3 arguments of it. The first one is this, the second one is this, and the third one is this. The first one is a makefile, which is actually a regular file. And in this case, it happens to be read. Supposed to, in this case, it's having read permission, reads, and that makefile happens to be 17 lines long. This is the subdirectory. This is the subdirectory. It should be says unable to read. Okay. On the other hand, if I specify something like this by star dot, static by star. Okay, start dot question mark. So this means some name followed by a dot followed by a single character. So these are the 1, 2, 3, 4, 5, 6 files that match. This all happens to be regular files and readable. So 11 lines are in this, 82 lines are in this, 17 lines are in this, 79 lines are in this, and so on. Happy? You need some practice, otherwise these things will not become very clear to you. But then it is anyway short semester. I have to teach you only in the last line. Okay, so any questions about this? If not, I will give you just the last example and stop today. Okay, maybe clear. Okay, so this is the final example that I am going to talk about. Now, what I do, I write a shell script, all matches.sh. I run it with a file name followed by a regular expression. Okay. And what this code will do, it will find all the matches of the regular expression in each line and it will mark that thing. Okay, so what I mean by this marking is this. So suppose I run this on our text file.txt. So the match starts with a capital letter followed by anything other than capital letter, any number of times, followed by a lowercase letter, a small letter. Okay. And all the matches of that file are written. So this is one match. In the second line, this is only one match. In the third line, this is only one match. Okay, this is also a match. And there must be some lines where there are multiple matches like this, this, or this, this. Okay. Here there is a match starting here, ending here. Here actually there are three matches. This, this, this. Okay. So when I showed this kind of matches using this lace which highlights those matches, okay, it does this, right? It highlights this next part. It highlights this I introduce thee. It highlights P, comma, blah, 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 blah to explain it. Do you remember that? But I want to write a shell script which itself shows, okay, I understand, I assume that the text file does not contain these symbols, square brackets, opening or closing, and all these matches are listed like this. Okay. I can run grep, but grep will only print the lines that match. It may also highlight these matches in some color like red. Okay, as it happens in my case, in my machine. But this is what I explicitly do. Okay. So this is the code for this. Okay, so you just compare this with the output of grep, the same pattern in it, and give text file.txt. This is completely created by me, and this is created by grep. Okay, so now let's see how we can achieve this. Okay. Okay. So I need at least two arguments, or two arguments actually, file name and regular expression. If the number of arguments is insufficient, simply exit one. Okay. Otherwise, the pattern that I keep on searching in a given line, read minus R line, and this while loop corresponds to this done, and this is read from this $1, the file name that I supply. This is read from that file on line by line. Now in each line, it searches for this pattern. What does it say? Take any string, dot star is any string, followed by $2, $2 is actually the regular expression followed by anything. So this is the pattern that I will keep on searching until a search fails. Okay, until this pattern search fails. Okay. So number of match is 0 for the moment, and T equal to an empty set, empty array. M is an empty array. M will store the matches, and T will store the text in between the matches. Okay. Now, as long as I can match, I will search for the line search for this pattern in the current line. And this is the operator equal to tilde, and you specify it within a pair of double square brackets. If the pattern matches, then this loop essentially breaks. You simply append that T to this array T. This is part of the text which does not match, break. Otherwise, whenever you make a regular expression search in this manner, there is a variable, there is an array that will be populated. Now, the first thing that are enclosed within a pair of parentheses will go to bash underscore regular expression match 1. So this part will go to the 1th index. This part will go to the 2nd index, and this part will go to the 3rd index. So this pattern is found here. So this is the 2nd element. So you append M by the match. Append T by whatever follows this match. And rename line as, or reset line as, whatever is here. So you will now search for another match, which is a previous match. So matches are stored in the array M, one after another, but this time it is stored from end to beginning. So if I look at this example, first this match is found, then this match is found, then this match is found, then there is no match. So the T array will store this. T array's first element will store this, or 0th element. T array's first indexed element will store this in between matches. Okay. Last element will store this. Okay. And then you see how many elements are stored. Number of matches is okay. N matches for storing the total number of matches in all the lines. Okay. So increment that by L. This is not 1, this is L. And you first echo the first segment which did not match, and then from L minus 1 down to 0. Okay, 1 second, this should be minus minus, then another LaTeX error. Okay, I will take care of it. You print the match followed by the non-match, whatever follows. Done. And then possibly this is echo minus n. So this echo gives a new line. Done. Less than $1. And total number of matches. So all these ALs are added. That's it. Okay. So total number of matches found is 25. Yeah. So that's it. This must be difficult. Any questions? Don't know. Then let me ask a question. Why I am printing it from L-1 to 0? Or in other words, why are the matches found from the end to the beginning of a line? Can you tell me? Okay, it's apparent that this will be the first match found, then this will be the second match found. In this line, this will be the first match found, and this is the second match, this is the third match. But why is it not happening like that? Actually, I am detecting this match first, then this match, and then this match. Why? Look at the regular expression and tell me. The regular expression is supposed to find the leftmost match, right? Why is it find the rightmost match? No idea? I don't know. So I am not searching for $2. I am searching for this entire thing, of which $2 is a part. Now I will find this regular expression operator, pattern match operator will find a match or try to find a match of this entire pattern. This is not just $2. It's dot star, $2, dot star. Now you apply this general, I would say, philosophy of Unix regular expressions. It should be the leftmost match, and among all possible leftmost matches, as long as possible. Okay, does it make sense?
Yes, sir.
Okay, so this is actually a way of finding the rightmost match. Okay, so that's it. Okay, so that's it. Any other question about this part of the code? This is once again a default array. Whatever happens within this, if you want to ignore this part, you just say dollar, I mean dot star. But I want to store that thing. Okay. So anything I enclose within parentheses, this will go to this default array. Bash regular expression match 1, bash regular expression match 2, bash regular expression match 3, and so on. It is not rematch. It is RE match, regular expression match. Okay, so eventually you can actually write a code like this. Okay, so what else? Okay, so because of, I would say, scarcity of time, we could not give you some exercise on shell programming, which we should have given, I would say. But anyway, you see that stitching these things continued until today. So now if we give an assignment, when will you submit? Your exams are starting from the next week anyway. Okay. Okay. Yeah. So if you have no other questions, let us stop.
Sir,
Yeah.
sir, can you please share, share any questions of the assignment? Sir, it won't be submittable, but we can have something to practice.
In that case, I would suggest that you look at some textbooks we will refer, right?
Okay, sir. Yes, sir.
The exercise sets you try to solve. One or two assignments, maybe one or two exercises. And I will figure, I hope the textbooks that we will refer has exercise sets. Yes, yes, they have. Sumita Das's book has exercise set. And the Sobel's book, I do not fully remember, I have to check. But as the Sumita Das's book has exercise sets. Try to solve some of those.
Okay, sir.
Okay. Okay. So any other questions? Not clear? So are these concepts too alien to you? Either you understood everything or nothing. So what is the case? It's just another programming language, right? I would not say programming language, it's a scripting language. It has its own for loops, it has its own operators, it has its own if then else conditions. That's the only difference, the syntax and the default operators. Okay. Anyway, I don't know. Today's class is apparently too, I would say, non-interactive. Okay. So if there are no further questions, let us stop.